Okay, so I'll just do the walkthrough of some of the exercises that we couldn't get through in the morning. I'm assuming everyone was able to, or a lot of you were able to launch a notebook and look at these exercises. So this is the one we looked at in the morning, and it's the first example of training. So the first step is importing all the modules, the Keras, H5Py, and the scikit-learn modules that are required. And each cell, when you run each block, it takes some time to run. While it's executing, you have a star here, so you got to. It's best to wait for the step to complete and then proceed. Because there could be some dependencies later on, and once it's finished executing, you get a number there, and then that means you can proceed to the next one. Okay, so this is the same the VGG16 model that we are using. So what we are doing is basically Keras has this model packaged within, and you can import it and load it. It's a pre-trained model. It's pre-trained on ImageNet dataset, and so what we're and this is the architecture of the model. It's basically doing a 1,000-way classification for images, and it was trained on the ImageNet dataset. And the architecture is as shown in the figure. You have these different blocks of convolutional layers followed by a max pooling layer, and what we are doing is we're augmenting this model after about, we're getting the output of after about block 5 for the pooling layer of block 5. And then we're adding our own fully connected layer and a softmax layer to do our classification into 3 categories instead of 1,000 that the original model was doing. So that's what this particular cell is doing. It's loading the pre-trained model. It's getting the output of the 5th block, the pooling layer of the 5th block. It flattens the output to a single dimensional vector, and it runs our then it creates our fully connected layer to do our predictions, and followed by a softmax layer to give us the probability for each class. And so these two cells basically set that model up for us. Set up the modified model for us. The next step is essentially so all of these layers have weights that are trained on a very large data set of ImageNet. So we are opting to choose to use those weights, and so we are basically for all the previous layers of this architecture that we're using, we're freezing the weights that were already learned from ImageNet. So we don't want to, during our training process, we don't want these weights to modify. So that's what this particular cell is doing. It's freezing those weights. And so during our training, the only weights that will be modified are the new layers that we've added. So that's what this step does. The next step initializes the Adam optimizer, which is a popular optimization function that uses some second order optimization techniques. And I think usually performs better than SGD. And then we are basically configuring the model with the optimization function, with the loss function, and the metric that we are going to optimize for. And then we can print the model summary, which gives us a line-by-line information of each layer. These are the last 3 layers that we added. The rest were, sorry, the flattened one is also us. And everything before that was pre-trained, was part of the pre-trained model. And then we set up the data input. So we use the image data generator API, and we're using the flow functions of this API. So basically, it assumes that you have the training and validation data set organized by, so within those folders, it expects subfolders for each class and examples for each class within those folders. So we have three categories. So in there, you have three subfolders for each of them. And each of those have examples for those specific classes. And if you don't want the order of images being fed, if you want to keep them varied, you can also turn on the shuffle parameter and also organize the batch size, which we have setting to 16. And so once you've set up the input stream, now you can call the model.fit function where you're giving it the training data. And you can calculate the steps per epoch by the total number of images here, right there, divided by the batch size for the optimizer. And so you get roughly 83 iterations per epoch. And so you give the model the fit function. You give it these options, and then it runs its training. It takes a few minutes to complete training, so you all can do it in your notebooks. This is the run from the morning, and here you can see the training accuracy and the validation accuracy. And you can see that there's a point where the validation accuracy sort of stagnates and the training accuracy keeps increasing, which is a sign that your model is overfitting. And we'll see. We'll run through the next example, which will show us one of the ways of how to fix this. So that's the first example. I'll stop it. I shouldn't have run the training. So I'll move on to the second example, which is just a variation of this.
Just focus on what's a variation of that, and just let people know what's the difference in them. That's enough.
Yes. Okay.
Thanks.
So almost everything, the setup of the network, all of that is the same in the second notebook. And so let me just run through it again. So same model, same data. The additional thing is this function so what we are doing here is we're using the image data generator Keras API. What this does is once you set up where the data is coming from, the folders, you can also do some transformations to the input data before it's fed into the neural networks. So before it's fed into the CNN. So for instance, here what we sort of add these, we've come up with this list with some experimentation, and it so you could give it a zoomed image, you could change its orientation, you could do a horizontal flip, and so on and so forth. And basically you're creating a variation in the input data set to possibly help learn newer features. So you're just weighting the input data set a bit in order to help maybe learning better features and then performing better on the validation data set. So that's the only thing that's different in this example. And again, it takes a few minutes to run, so I'm not gonna. You can run it in your individual notebooks. And in this case, that you can see that the the training accuracy and the validation accuracy. The training accuracy does not um, uh, keep increasing after upon more training, and the both training accuracy and validation accuracy stabilize. So there's the signs of overfitting were removed simply by augmenting the input data and using exactly the same model. So with a slight variation of input data, there was the way the model, the way the neuron weights were optimized slightly better to perform better on the validation data. So I'll move on to the third variation. Oh, sorry. Is it still sharing? No. Okay. It stopped sharing for a second. Okay, I'll move on to the next variation of this. And the third variation is basically showing you a customized um, customized loss functions, and also it also shows you example of the checkpointing API of KLOS. So again, the setup is mostly the same. Um, we're just running through the first few cells to set up the model the same way. This still has the data augmentation. So the following part is what's different about this third example. Here we are using categorical cross entropy as our loss function, and we're using something called label smoothing. So with the classification examples, what happens is if it you either get a classifier sort of gives you a 1 or a 0, and you don't get anything in between. And so if there are mislabeled examples, it leads the classifier to make the wrong classification with basically a very high confidence. It tells you with certainty whether it's in one class or not, and there's no notion of anything in between. And so one way to deal with a data set that has some data mislabeled is to use this label smoothing technique. And what that does is it has a hyperparameter for label smoothing, which you set in the loss function, and um, um, so these are so the label the categories are basically what are called one hot labels. One hot labels is basically in the vector of classes. You just have one bit set, you can say. So it's either one category or not, and it sort of distributes by the label smoothing factor. It distributes this across all classes, so you get like a probability across all of the classes. So if there's a wrong label that's fed into the data, it has it doesn't its effect is sort of spread across all classes, and it's not could overall over many layers prevent propagation of this wrongly labeled data sample. So that's what these functions are essentially doing. The next function is basically checkpointing of your model. It's an example to how you can write it out to a HDF5 file format. And after you've trained your model for many epochs, you could save the weights into this file. So that's always good practice. So you don't lose all the, you don't have to rerun it if let's say you're in a cluster and your job time runs out. You can still checkpointing is a good practice, so you can pick up training where you where you left off. Also, there's another checkpointing, another instrumenting API from Keras, which is basically reduce learning rate on plateau. So what this does is basically when it's exploring the loss surface, looking for a local minima, um, if there are a certain number of epochs which they define by the patience. Patience is basically if for 5 epochs in this example, there has been no change in the weights, then it could mean that we are close to a local minima and we should reduce the learning rate. So basically, when reduce the step size by which we change the weights of the neural network. So, and you also have a minimum learning rate that you can set that while changing the learning rate, you don't go below this. And you change the learning rate by what amount. You can start dropping it by 0.1. So those are the 3 main arguments to this function. And then the last step is again just to train the model. For this one, to see the effect of label smoothing, you would need to run it on for many epochs. But however, since we are running on Stampede 2, which we are running on CPU, it's quite a bit slower than GPU. I therefore set this example to 3. But when you're playing with this example, you want to increase the size of, increase the training epochs. And then observe the effect of what label smoothing has on your final prediction, on your validation accuracy. So those are the 3 main examples. The last one is basically an inference example. So let me just open that one up. So once you have a trained model, now you can build a kind of a prediction application around it. So that's what we do here. And again, we're running through the steps of defining our loss function, and we load a pre-trained model. So something that was the output of the checkpoint function in the previous example. We load that model in. And then we get we pick up one sample from our validation data set, or you can pick up any image, anything you want to predict on using this model. And then run the model.predict method on it. So to see which category it falls into. So this example, again, to remind everyone, it's trying to predict how damaged a particular residential structure is. And they have 3 categories of prediction. So low damage, I guess, medium, and very badly damaged. And this last notebook is just a small application to test prediction on any image. And so this is just something you can keep playing with. And so the top 3 cells are, top 3 blocks are basically just doing it for specific images. And the last block is doing this for a randomly selected image. So you can keep rerunning the last block to just see, just see random samples of how it predicts. So it says this one is not damaged. The previous one was heavily damaged. Sometimes it could be a photograph of a garage and it thinks it's very damaged because there's no doors or something like that. So you could see some of the ways that it's accurate, and some of the corner cases where it's not so accurate. So this is just an example for you all to play with the parameters, try it out for yourself, try it out for your own, for different data sets. So these are just to illustrate what can be done with the notebook and these this software stack. So with that, I'll conclude and won't take too much time from Zhao's session. And so these are all single node examples. And I think Zhao's session will cover more advanced topics on how to use multi-node training for very large data sets and so forth. So I'll take any questions if there are any, and otherwise I can hand off to Zhao. Shall I stop sharing?
Yeah, let's just do switch. Zhao, are you ready?
Yes. Let me share my screen. Cool. Shall I start?
Yeah, just go ahead.
Okay. Hey, everybody. So yeah, so my name is Zhao. I'm a computer scientist working at Texas Advanced Computing Center. I have a HPC background, and these days I work on the intersection of HPC and deep learning. So the outline of my talk will be first covering AI in science, basically give you guys a motivation why we are doing deep learning on HPC and for science, right? And the second part is about scalable deep learning, particularly about optimizers. And third part will be some practical work we have done to enhance the I/O performance of scalable training so that we can run large-scale DL training on supercomputers without incurring like I/O problems. Okay, cool. So this is a slide I stole from Kathy Alec last year. So this is showing artificial intelligence is driving application for exascale machines along with simulation and big data. Well, there are three pillars applications when these people are designing the next generation supercomputers, and artificial AI is definitely one of the driving application pillar in their design. So what can you do what can you do for your own research with AI, right? If you look at these four categories, we have data analytics, like if you can form your research as a classification problem or regression problem or clustering problem or dimensionality reduction, then definitely there is an opportunity for us to leverage AI technology or deep learning technology for this type of research, right? And I do know some researchers are looking into inverse problems, like I know some cosmologists are exploring deep learning techniques to simulate the the universe. They're simulating the universe. Okay, and they were trying to formulate that problem as an inverse problem. And sometimes you may need a surrogate model, like if the simulation in your research is too expensive to run on some on HPC, like it may take weeks or months to do a single simulation, then maybe there is a way for us to train a surrogate model which has much lower computation cost, but within certain error, with certain error bounds. Okay, and if you're controlling an instrument in your research, then there is definitely the opportunity to explore a deep reinforcement learning to operate the instrument like in a smart way. It's like just like operating a for example, a astronomical telescope, right? So here comes my example. Like I'm also involved in a astronomy project. Like we're trying to design a sharing platform for a lot of telescopes to cooperate on a single task. Okay, so if you look at this model, it's almost like being used anywhere. Okay, so let's start from here. We have telescopes and detectors, right? these instruments are collecting data. On one hand, we send this data to storage, like we're archiving the data, and we can process the data to, for example, to clean the data, to calibrate the data, right? Then we feed this data into a training module. Like we have a task we want to do, for example, to detect the transients, like for example, supernova explosion. We want to detect this from the astronomical images, right? And we train a model. Okay, once we train a model, we want to deploy the model that is to be close to the telescope, so we can do real-time transient detections. Okay, so once we detect these events, then we have a centralized controller or distributed controller to coordinate different to coordinate telescopes or other detectors to focus, saying, hey, there is an interesting event. If you would like to focus on it, now is a good time, right? So this is like data-driven decision-making pipeline. If you think about how, I'm not sure how many users are using Amazon Echo. Like Amazon Echo can definitely collect voices, right? In foreground or background, right? And after they collect some voices, they will transfer it back to some storage place, right? And they clean the data, they train a model. While they train a model to better send you advertisements, right? And they serve the model in the Echo, right? And based on your reaction, they label these predictions and feed them back into the training process. So it's basically the same. It's basically the same pipeline. Okay. So when we store the data, we probably care about persistence versioning, and when we process the data, there's definitely like domain-specific data processing workflow we want to run. And when we train, we care about how frequent we update the model. We care about the robustness in training and validation. And once we deploy it in the wild, we care about prediction latency, and we also care about like the real model performance. Okay, so this is an example of how we are using deep learning in scientific research. Okay, and if you look at this part, like these orange rectangles, like these can be far from telescopes. Then this could happen in data centers, like our Texas Advanced Computer Center, right? And the blue parts are deployed, can be far away. They're in the site, okay, in the fields. Yeah, that's, people often call this model like edge computing, right? The blue parts are the edges. Cool, cool. So yeah, so I would like to motivate you guys to think about how using AI can benefit your own research. It's like how we can formulate your research problem into one of AI's paradigm. Okay, cool. So next part, we'll be talking about scalable deep learning. I'm sorry about the background. Baby's crying. Okay, so why would someone train on multiple nodes? So we already have very strong nodes, right? We have very powerful nodes. We have one node with several GPUs, but why would someone still want multiple nodes? Well, in reality, training a model is very expensive and very time consuming. It can take weeks or days to train a single model. So definitely want to reduce the training time to enhance productivity, because it's not just you train it once. In reality, you have to tune the hyperparameters of a model, and that requires maybe hundreds of thousands of trial runs. That you train it, you see the results, it's not right, so you train it again. So it's a trial and error process, and it can repeat for indefinitely many times. Okay, and the other reason people are using multiple nodes is like sometimes people have a really large model, and this model simply exceeds the memory limit of a single device or single GPU or CPU, right? So they have to partition the large model and deploy them onto different GPUs and do like, they leverage all these GPUs for training purpose. Okay, cool. So when we talk about distributed training, there are 3 ways we can do it. Data parallel one is probably the most widely adopted approach, and the model parallel is now a thing. And hybrid parallel is like, I've seen them, but I don't see a lot of people making real good use of it. Okay, so let's jump into this data parallel. So in this data parallel model, it's like we have a batch of training data, right? And we replicate the model across different nodes. It's like here, like node 0, node 1, node 2, they store the same model with identical initialization of values in these units. And then we feed different batches of data into these nodes. So I use different color scheme across nodes, okay? And then we run feed-forward computation. We run this in a forward way, right? And in the end, each node will have a different loss. And we can use a loss to compute gradients of the loss with regard to different parameters, right? And at this time, all these nodes start to communicate. We're trying to compute the average of the gradients across the nodes, okay? And in MPI, in parallel computing, this is a collective, there is a collective data movement operation called R-reduce, which we can call to compute the average of all these gradients. And you see after this communication call, I use green color for all these units because every single node will see the same gradients, and they will apply the gradient descent rule to update every single weights in this model. So at the end of an iteration, all these models are identical across nodes. So basically, this is data parallel. It's just a R-reduce operation right after the forward computation to average the gradients. Okay, so this is data parallel. And the good thing is, like in the forward computation phase, this parallel model can make really high utilization of available nodes. But as you can see, those backward computations are identical to each of the node, but it takes relatively a smaller portion of training time. Yeah, so this is data parallel. Most of these popular deep learning frameworks like TensorFlow, PyTorch, or MXNet, they support this data parallel approach natively. Okay, cool. Yeah. Okay. So the next thing I'm going to talk about is model parallel. So now we have two nodes. I mean, let's say the model is very large, okay, and it's really hard for us to host it on one node. So we partition the model and let each node hold half of the model, okay. And obviously there have to be some communication between these boundary layers, okay. So yeah, but the idea is similar. It's very similar. It's like we run forward computation from the very beginning of the graph, then pass it through. If this arrow is a boundary, then it's a message. We send it to the rest of the nodes, but it's probably in a much smarter way, right? And all the way we get lost, then we start to compute gradients and update the weights. And similarly, we still need a communication phase between the nodes in this boundary, okay? And then people come to this situation like, okay, even though my model is not that large, can I still partition the neural network and put it on different nodes? And for some nodes, data parallel is more effective, but for some nodes, it might be not. So here comes the pipeline parallel. So here we have two nodes, and this arrow is a timeline. So we still have batches, right? So let's say the first batch 0. Node 0 will run forward computation for batch 0, running halfway through the network, then send it to node 1 for the rest part, right? And then node 1 will have this batch 0 backward computation, and halfway through, then goes back to node 0 to finish this iteration. So what pipeline parallel does is like this. We can still run multiple batch, right? So node 1, 0 will run forward for 0, then passes to node 0. And then at the same time, node 1, 0 is idle, right? So we can feed another batch. We can feed another batch to node 0, and in this way. And once we can accumulate the loss, once we accumulate the gradients, we can do backward for the second half of the neural network, and then all the way back to node 0 to complete the iteration. So this is J using using a larger batch, and in system implementation is much more complicated. This is synchronous, and last year there was an OSDI paper. If you see if you look at this parallel model, it's not as efficient as data parallel, right? And so these people look into a asynchronous SGD implementation by by further mixing these computation units and to reduce the training time. But again, if you're using asynchronous SGD, it's not always guaranteed to converge. Okay, but this is showing a simple example. There is such a way called pipeline parallel that some system implements, but the applicability is sometimes not very obvious. Okay, and the next thing, the last parallel model is hybrid parallel. So I give a simple example. So you can partition a model based on different layer. For some layer, you use data parallel, and for some other layers, you use model parallel. You're trying to take advantage of the communication and computation ratio in this case, trying to reduce training time, but as a high-end user, you probably don't have to worry about this. And there's another way for hybrid parallel. Think about, we have a lot of compute nodes, right? So first we divide them into groups. We let each group running a model parallel, and the intro group will running data parallel. So that's another way for hybrid parallel. So we're not, that's just another way, yeah. I don't know of any like real example people are running training neural networks in this way, but it can be implemented given certain circumstances. Okay, cool. So to summarize,
there's a question in chat.
Sure. How are the stages in pipeline decided? Are they dynamically selecting? Well, for the works that I know of, okay, so the question is, how are the stages in pipeline decided? Are they dynamically selected during runtime based on the model and input size? So that's the question. The answer is, based on the work I know of, they usually require a profiling stage. Okay, and they can do some planning to do a graph cut to minimize the communication between nodes. And there are also different boundaries, limitations they apply to this problem. But yeah, you probably need to profile this graph, beforehand. Yeah. I wouldn't say it's very practical, very practical approach. Yeah. Cool. Yes. Okay. So to summarize this distributed training paradigm, so data parallel is widely adopted by popular deep learning frameworks such as TensorFlow, PyTorch, and MXNet. And at TACC, we support Harvard, which is a communication framework that supports both all of these three neural networks. All of these three frameworks for distributed training. Model parallel is applied when model exceeds memory limit. Pipeline parallel assumes model being distributed across nodes, and each node holding multiple versions of the model is often used with asynchronous optimizers. So in reality, I think if you want to start with deep learning research, if we want to start using deep learning, I would say you start with data parallel, unless you have a really large model, you want to try model parallel. Yeah. So unless you're a CS researcher, I wouldn't recommend starting with pipeline parallel. Yeah, okay, cool. So yeah, deep learning and HPC. So from a HPC perspective, when we look at a type of applications, we care about three things, right? Computation, communication, and IO. So if you look at this data parallel implementation of deep learning frameworks, it has these three parts too, right? So DL training is computation intensive, especially when we have this convolution or LSTM or transformer. But HPC has massive computing power by composing a massive amount of processors, CPUs, GPUs, and there are customized ASICs that are optimized for matrix vector computation. Yeah, so that's perfectly fit for HPC, right? And there's communication part. The backpropagation algorithm is dominated by the all-reduced operations from previous studies. Yeah, I put here some overgradients, and once you have the sum, you can compute the average. So while HPC has this low latency high bandwidth interconnect, which is a great fit for this type of communication. And in my own research, I also do second order optimization, like using chronometric factorization to approximate the feature information matrix. And that method requires even more computations. It requires more communication for the approximation. And using interconnect on HPC, well, it's just great for performance. Okay. And the third thing we care about is I/O. Well, this is often like overlooked by users. It's like the massive I/O of DL training sometimes can be really, really problematic on conventional shared file system on HPC. If you think about the ImageNet dataset, we have about 1.3 million small images in about 2,000 directories. And the way we're accessing this directory is completely random, right? So every time we access, in every iteration, we access a batch of the data set, right? And theoretically, the selection of this batch is independent with other iterations. So it's really hard to find a way to efficiently cache or prefetch this data set. And if we run a 16 node, each with 4 GPU on this workload, it can easily slow down our shared file system, and sometimes it causes the file system to hang over there. I will talk about this in a lot of details, and we have some solution for this. Cool. So state-of-the-art results of deep learning on HPC. This is not state-of-the-art anymore. So in June 2017, Facebook researchers published a paper. They were able to train this ResNet 50 neural network for 90 epochs in an hour. And we collaborated with some researchers at UC Berkeley and UC Davis, and we leveraged the LARS algorithm, and we were able to train the same thing with 20 minutes on, using 2000 Intel Xeon scalable processors. And about a month later, some researchers from Tencent and Hong Kong, they were able to reduce the time to 6.6 minutes. And then Sony researchers bring it down to about four minutes. And then Google were using 1000 TPU to finish this part of training in 2.2 minutes. I think the latest result is about 56 or something seconds. Yeah, it's within a minute. Yeah, so we were happy to be part of this silent competition. And all of these subsequent works are using the algorithms we implemented on Intel Xeon scalable processors. Yeah, and this is just for ResNet 50. My collaborator also works on BERT, so the language model, which is transformer layer driven, and they were able to finish that. I can't remember, maybe 18 minutes on 1000 TPU v3 pod. Yeah, something like that. Cool. So to basically showing, so what I'm showing here is running deep learning on HPC is a great decision. So it reduces the training time significantly. Okay, cool. Okay, so now it comes to the last part of my presentation is about scalable I/O. Am I speaking too fast? Yeah. Okay, cool. So scaling SGE. So to efficiently leverage the computing power on HPC to reduce the training time, we need to use a large batch size. So the reason is like this. So let's assuming we are training with batch size of 128 on one node, and that takes time t. If we can train with batch size of 256 on two nodes, ideally it should take half of t to finish training, right? So that's something is ideal. But in reality, it's not like that. So with larger batch sizes, the validation accuracy or test accuracy is going to degrade with larger batch sizes. And researchers have summarized a set of techniques to fight this situation. One is learning rate linear scaling. The intuition behind this is if we are using let's say a batch size that is twice large, that means we are updating the parameters like half of the frequencies, right? So that in each update, we should update twice as far as we used to do. So that's why we're linearly increasing the learning rate with the baseline batch size, okay? So the second method we always use is warm up. So if we're using a large batch size in the very beginning, that's very easily to trap the optimization in a stale state and never comes back. So when we start training, we start with very okay. So for example, we warm up for 5 epochs. That means for the first 5 epochs, we start a learning rate from 0 to our target learning rate linearly through the steps, and we warm up this training phase. We warm up the learning rate through the training phase, and in this way, we can escape the stale states if without this warm-up technique. And the third thing we tried is layer-wise adaptive rate scaling. So if you look at deep learning training, if you look at neural network, they have so many layers, right? And all these layers have different magnitude on their values. And using a uniform learning rate across layers doesn't seem quite to make sense, because for some layers, this learning rate is appropriate, and for some other layers, this learning rate maybe is too large or too small. So once we compute a learning rate, once we have a learning rate, we can always scale it down or scale it up based on the norm of a particular layer. So that's the intuition of this method. Okay, so I will present some very, very simple training example with these methods. Okay, cool. So this is an example we have a hands-on of this. So to train a ResNet 20, it's a residual network with 20 layers on the CIFAR 10 dataset. It's very simple, very small dataset. It only has 10 categories. Each of them have 5,000 images. So in total, it has 50K training images. If we were using batch size 128, you can see that's the blue curve. It trains like this for the first 20 epochs. The validation test accuracy is it's over a little bit over 60%. Okay, and if we double the batch size, which is 256, what we observe is here, right? So yeah, it's the test accuracy by the end of 20th epoch is lower than the previous case, right? And if we map this into time, ideally, that means in half of the time, we couldn't reach the model performance that the original case reached, right? So what shall we do? So now the first thing we want to try is learning rate linear scaling. Again, the intuition is doubling the batch size results in half the frequencies of parameter updates. Thus, we should double the learning rate to mitigate this. And a simple way to do this is to just simply double the learning rate from lambda to twice of the lambda, right? Learning rate, batch size, yeah. So this is what we see with the learning rate linear scaling. Again, this blue line is batch size with 128. The green curve is batch size with 256. And this yellow case is with linear scaling, but we see it's not that good, okay? It's not that good. And then we try the next thing, is warm up. So the intuition, I would say, just read it again, like larger learning rates may lead to the optimization to stale states. Starting with small learning rates, then gradually increasing to target value may be effective. So let's see, the target learning rate here is 0.2, and we are warming it up for 2 epochs. The sample size is 50,000, batch size 256. So for each iteration, the learning rate can be computed in this way. So this is just a linear scaling. it's just a linear operation. And we see this red line, the red curve, is batch size of 256 with linear scaling and warm up. We see is slightly better than what we have with 128 batch size, right? So by the end of 20th epoch, yeah. And this is good enough. And we also try this LARS, a layer-wise adaptive rate scaling thing. It's a little bit complicated. So here is generally the SGD rule. We use a momentum of 0.9 to learn from old values, and we scale this learning rate using a scaling factor. Lambda is still the learning rate, and this part, the normalization part, is how we calculate the scaling ratio of each layer. Okay, and we are using a weight decay to kind of like to control from the history. Okay, and anyway, when we use this, so when we combine this learning rate, warm up, and LARS, we can see this training curve, training performance is much better than all other cases, right? So, yeah, but there isn't a theoretical proof that using LARS can improve the convergence rate algorithmically, but in practice, this is what we see. But if you talk about the convergence target, it doesn't change much. It doesn't change much. Yeah. Cool. So this is, and if you reproject this training time, this training performance into time thing, this is not epoch, I'm sorry, this is time. So we were able to reach to a better place than a smaller batch size using half of the time. And this is the point why we're using large batch size and why we're using multiple nodes, okay? Cool, so here's my recommended practice when you train with multiple nodes. First, you're gonna figure out the default batch size. It's really from the literatures. If you start from, for example, if you look at design safe case we just show you in Amit's session, we use a VGG16 model, right? So that's something called transfer learning. So this VGG16 model, they train it with ImageNet dataset, and those first layer, those layers before the linear layer, the fully connected layers, can be understood as feature risers. So think about this: you have an image, you feed it through VGG16, you will get a list of vectors. Sorry, you get a vector of elements to describe this image, right? So that's the featureization process, and usually you can get this default batch size from literatures that are related to this, like VGG16, ResNet, or AlexNet. Yeah, so yeah, that's a good way. That's a good point to start. Figure out the default batch size, and on a single processor, run the training program with default batch size, and observe the processor utilization. So if you're on a CPU, run the top when you're training. If you are using a GPU, then use NVIDIA SMI for GPU. So here, in the CPU side here, we're using 26 cores, right, out of 48, or 56 on Skylake, right? And if you're training on GPUs, you can tell the utilization from here. Just make sure on a single node that you are saturating these computation resources, okay? Cool. So if the utilization is low, you can try increase the batch size while preserving the test accuracy till the processor is efficiently utilized. Either RAM or compute is saturated, right? Then you can try scale up. You can try learning rate linear scaling or combine with warm-up technique. Usually you do with warm-up. Yeah, and once you're at that stage, you can scale up to multiple processors and multiple nodes with LARS, or they have a later version called LAMP. You can try this. And we also did some research on second order optimization with Kronecker factorization. That's also scalable to some extent. Yeah, to like 128 GPUs efficiently. Yeah. So you can look into other optimizers. Cool. Okay, so that wraps up my presentation about this teeter stuff. Like, first we talk about how to use Oh, okay, cool. Sorry, I forgot about this IO thing. Okay, so this is why we're doing multi-node training. Okay, and once we do this training on a HPC machine, there might be some problem. So let's look at here. Resident 50 training on ImageNet, 1.2 million image files in 2002 directories. We were using Kira's TensorFlow and Harvard. We scale it from 1 node to 4 nodes to 8 nodes to 16 nodes. Each node has 4 NVIDIA 1080 Ti GPUs. We place data on Lastre, and here's what we see. So the throughput is images per second, the higher the better. And you see from 1 node to 4 nodes, the performance gets worse, right? And to 8 nodes, well, this gold line is the linear scaling performance. It's a target, it's the ideal case. But we can only achieve like 50% on 8 nodes and maybe about 30% on 16 nodes, right? The scaling efficiency is very bad. This is due to the Lastre file system metadata management implementation. So this just doesn't scale. Cool. So why Lastre is slow? Because this distributed deep learning training has massive and highly concurrent metadata access, and it also has massive and highly concurrent data access. If you're not a CS researcher, it's okay. You don't understand metadata and data, but just keep in mind, running DL training in the distributed way with data on share file system may cause you some problem. Okay. And we also see that global dataset view is critical. What is a global dataset view? A global dataset view is we are using multiple nodes, right? Global dataset view is like every single node should see the same dataset in terms of the categories and number of images. Because there is a intuition that, okay, if the data is too large, can we just partition them into different parts and let each node train on different part of the data? Okay, so that in that case, each node only sees a partial data set. So that is a local view. That's not a global view, right? And what will that lead into is divergence. If you look at this yellow line, for this Resident 50 training with the same number of epochs, we can only run to like 70% validation accuracy. But if we train with a global view, that can run to 74 or something, right? We showed this not for the performance of Resident 50 because the MLPerf benchmark requires a 75.9. We're just showing here like a global view and the partition view makes a difference. So global data set is critical. That's why people are placing the data set on the shared file system because every single node has the identical data set view. And yeah, and that will cause some problem, right? So what our solution is to leverage is local storage and the interconnect to reduce the IO traffic between compute nodes and the shared file system. So the nodes on our machine have some local storage space. On Maverick 2 cluster, it's very small, it's about 60 gigabytes, right? But with multiple nodes, we can aggregate those storage spaces and build something like a shared file system. We call it object store that provides a global namespace. So in that case, we aggregate the local storage space of the nodes and making them work as a shared file system, okay? Cool. So we place the metadata and file data across nodes to enable high performance read and write. And we preserve a POSIX compliant interface for users' convenience. So that means through some way, we can expose this shared file system using a POSIX compliant interface that you don't have to change your program interface to access data. You can just simply replace the data path. Okay, we have an example. So in this way, we can enhance the storage capacity of existing hardware with possible compression. Okay, and our solution supports x86 and Power 9 architectures. Cool. So this is the architecture of FanStore. So on the shared file system, we need to do some pre-processing. We have the data set, right? So after the pre-processing, we separate the metadata from data set, and we also partition the data set in different partitions. And upon execution, each node here will load a distinct partition from the shared file system, but the metadata will be broadcasted to all the nodes. So, and the metadata keeps track of where a single file system, where all the files are. So for some of the files on this node, for some files in this metadata, some of them are local, right? And some of them are global. And this metadata includes the location information of the data. Okay, and we also maintain the L cache and a metadata cache. And the interface of this FanStore, we use a function interception technique that we dynamically intercept the glibc IO functions and to supply our IO logic instead of the shared file system IO logic. And what DL applications see is still the same, okay? Cool, so let me summarize. Data is partitioned and spread across local storage space. Metadata is replicated in RAM. File access functions are intercepted and handled in user space. So you don't need root privilege to install this. And the remote file size is in the form of MPI round trip message. And local file access is simple, right? Cool. So with this, here is the performance. So we trained ResNet 50 on ImageNet dataset, use the same Keras TensorFlow hardware framework. We scale this thing from 1 node to 4 to 16 nodes with 4 GPUs each. And here you can see this blue bar. We are almost like 90% efficient compared to the ideal scale, linearly scale value. And our baseline is 1 node. Okay, our baseline is 1 node. Yeah, in 1 node, there's no distributed overhead. There's no distributed overhead, but still we have about 90% efficiency. Okay, so this is our solution. So with FanStore, no need to change data access method in TF or PyTorch program. It's POSIX compliant. It can reach like 70 to 100 read performance compared to raw hardware. And it increases the processing capability of the existing storage hardware and enables efficient and scalable IO for distributed training with millions of small files. Okay. And to use it, you can simply just export it, a environment variable like this. And when you launch this training program, you do MPI exec using a host file that includes all the hosts, launching a certain number of processes. And yeah, just the way to launch FanStore. And we intercept this glibc IO operation through LD preload. And dataset then is accessible through this POSIX path. So you can just supply this path to your training program saying, okay, my training data set is here. So we'll read it as it reads from a shared file system. Okay, cool. So FanStore is available on TACC, STAMP2, Maverick 2, Frontera, and Longhorn system. And the x86 source code is available on GitHub. And if you run into a case you want to use FanStore, you can send me an email and I will try to help you to set everything up. Okay. Cool. To summarize my talk, like we talk about how AI can help scientific research, okay, and how you can formulate your own research into an AI problem, okay. And second, we talk about scalable deep learning, as we talk about different distributed training paradigms. We talk about optimizers. We talk about some techniques to help you scale training across nodes, right? And the third part is scalable IO. It's like we briefly introduce why there is a problem, why IO is a problem, and how we solve it with FanStore, okay? And in reality, if your training data set is small to fit in a local disk, just copy it to /temp. Or some local disk on other machine and train from there. To try avoiding loading the data from shared file system is always good practice. Okay, cool. So that summarizes my presentation. And next, I'm going to give you guys some hands-on. So you can start with this. You've already logged into STAMP2, right? So first thing is to copy my training directory into your own place. You can run this in a notebook.
Quick question, Zhao.
Sure.
So Frontera is not up, I'm guessing. So we are continuing with Stampy.
Yes. I don't think we have a reservation on Frontera, do we?
No, I think Vijay mentioned in the morning that
We do have a reservation on Frontera, but in this noon, the Frontera queue was down again. So I wasn't sure if it's fully back up yet. So let's just go ahead to with the Stampede reservations. And if you guys are interested to try Frontera, it's actually the same process when you start the Jupyter Notebook. And then when you start the Jupyter Notebook in the Wiz portal, there was different resources available. One is Stampede 2, and there are also Frontera. So for the Frontera, you basically put in the same information, and you can try to start a new Jupyter Notebook there as well. The rest of them is almost the same, but the only thing is you need to put the data, because the data we're currently available is also only available through Stampede 2. So let's finish it using Stampede 2. So if you guys interested and you have more knowledge with the system, how system works, you may give it a try with the Frontera. But right now the Frontera is not really very stable to use. I'm sorry.
Okay, no, yeah, thank you. I just was checking. There might be some users who might be interested, and we can.
Yeah. I mean, for deep learning, training on GPUs is a lot of fun. On CPUs, it's not. Yeah.
Okay, thank you.
We just had this problem on Monday. We had some power outage problem, and then it's causing a lot of things. And now it's a kind of downtime for us. And
cool. So once you copy this directory, you can go to Jupyter Notebook. For me, it's like, this is my home directory. I go to UTSA, then apps. You will see 4 notebooks. The first one, sorry, the untitled one is my example command to copy over. Yeah, but you need to install Harvard first. I open it up here. So it may take a while. It may take a while. You can just run these 2 lines. Yeah, it may take a while. Yeah, sometimes I have to keep my eye on this symbol, make sure it's running. It's running. It's just slow.
Zhao, I think someone in the chat wants to see your first command, the copy.
Oh, this one. Easy. I can put it over here.
John Weija, it looks like the RTX queue on Frontera is online right now.
Yeah, but this example won't run on it. So this example is customized for Stampede 2. I haven't tried it on RTX yet. I think it should work, but just like we have some CPU optimization in the script here.
Okay. Yeah, because there's still a reservation available. So if you do want to give it a shot.
Yeah.
So if you want to give it a shot, and what I recommend is you may actually try the notebook we have for the morning sessions. The only
Yes.
thing is that you need to copy over the data sets and the folders and into Frontera Scratch as well. Or we also have one copy there, right?
I think so.
I did
I
have
mean,
a
it probably
copy,
has it.
but I did have a copy on Frontera before it went down. But the difference is in the installation step for TensorFlow, we installed the TensorFlow GPU. While on Stampede, we used just the CPU version for TensorFlow. So that's the one setup that will change there.
Okay. So Amanda, can you update the location on the Frontera? So
Sure.
just
Sure.
and if you need to change the install, like the setup scripts to specify using the GPU with the TensorFlow on Frontera, just you can change that too. So we can just put the link up there.
Yeah.
Okay.
If you want to
Cool.
try.
So now Harvard is installed. In my case, if then next open this run cipher10 first sanity check. The first command is to load modules and copy data to dev SHM. So dev SHM is a RAM disk. So it's like a file system thing, but it's in RAM. So since this data set is small, it helps us avoid traffic to a shared file system. So run this, then try this Python 3 cipher10 ResNet raw thing. If everything is correct, you should be able to see the process here. Epoch 1. Yeah, see, my program starts to train, and this ETA is the estimated time for this epoch. It's not very fast. It's about 27, 25, over 20 minutes, right? So that just gives you a sanity check, everything runs. So kill it. Kill it. Cool. And you can run the next thing is with some Intel handcrafted optimization configuration, we'll just print a lot more things, right? So here you should be able to see a shorter training time. See, the training speed is much more faster than it used to be, right? See, now the epoch takes about, I don't know, maybe a minute to finish. And by default, this command line trains with batch size of 128. Okay. See here. See, my first epoch takes about 45 seconds, which is much faster than it used to be. And this is Intel handcrafted optimization environment variables. And you can, okay, so I'll kill this. You can run it and look at the next cell. I said modify line 344 to change the batch size from 128 to 256, right? And it will still take the same time, but it will guarantee you using a large batch size. Well, it will show you using a large batch size will give you a lower validation accuracy. So if you train here for a number of epochs, cool. So yeah, so this is an exercise you guys can do. I'll kill it for now, and I'll come back later. Okay. So if you look at this exercise, like scaling thing, since you already copied the data sets, you don't have to in this notebook. Let's say this exercise run the ResNet 20 example with warm up, okay? And the next cell runs it with LARS. So if you are running things correctly, you should be able to see what I have shown in my previous slides. Let me show you again. Let me show you again. Share screen slides. Okay. Cool. You should be able to see. Okay. You should be able to see this. Yeah, you should be able to see these curves. Okay, but you have to plot these curves. This is what I plot with the validation accuracy. You should be able to see these curves. And the last thing you can try is to run on multiple nodes. We've talked about running on multiple nodes, but we didn't ask you to try. So here is how to do it. So in that way, you have to log into STEMB2 using a terminal. So SH to STEMB2, go to your home directory, UTSA apps, then you can using sbatch dash reservation UTSA, then run cipher10 res and harwa.slurm. So if you look at the slurm file, sorry, share screen. Yeah, this is my favorite way. So next. If you look at here, we're submitting the job requesting 2 nodes, 2 processes into SKX normal queue running for 20 minutes. Using this project, you guys should have access. And we're setting some environment variables to boost the performance, load the module, and then we copy the data over. And the very last line is to launch the training process. We're running 2 processes on 2 nodes, and the IB run knows how to assign the process to different nodes. So each node will launch 1 process. Running this Python 3, cipher resonate harwa LARS, this program, each process uses a 128 batch size. Okay, so this will run it. And you will be able to see the results in this log file. For example, if I show you in my 2056, oh, sorry, curious. So here is what I see. So everything is printed twice, but not this process. Okay, here you can see it will run. And here, finish 1 epoch. Yes, see, each epoch only takes about 23 seconds. If you see what I've trained the previous example in notebook, it takes about 1 minute, right? Now, well, because the first epoch always takes longer, the second epoch will take about 40-50 seconds. And you see with 2 nodes, we can actually run it twice fast per epoch. And that's, yeah, it's always 23, 22, yeah. So that's how we do it. So simply you just do sbatch to run on 2 nodes, okay? Nice, so let's go back to, let's go over the slide, see what is left. Okay, so hands-on, open notebook, copy the data over, then install Harvard, then run the cipher10, then cipher10 scaling, then multi-nodes. Okay, cool. So I think that's all my presentation. I can take questions.
Yeah, I think some of the students were not able to get to the folder. There were permission.
Oh, really?
Right?
Really? Let me see. Okay. Oh, shoot.
Joe, you're not supposed to share your home directory.
Oh, really? Then let me move it somewhere else.
Can you move it to the Scratch directory that
Yeah.
I'm using this morning?
Yeah, you'll mess up your SSH keys if you do that.
Oh, yeah. Okay, UTSA. That's my terminal? No, right? Okay, so copy this over. Sorry. Okay, copy this over. I'm sorry.
For posterity, after the lecture, Zhao, do you mind updating your notes with that path? I don't know if that's going to be a permanent directory, but it'd be nice.
Oh, you know, I'll leave it for a while.
Okay.
It's not large, it's a small thing. Yes. Question. Unable to access folder. Oh, I see.
Yes, that works.
Yeah. Well, if you really run, okay, so we are showing example using Keras over TensorFlow. But if you are trying to program with TensorFlow itself, you will experience a lot of weird things. Like like the batch normalization, when you do a checkpoint, it doesn't automatically record the running average and the running variance. Every time you restart training from the checkpoint, everything goes weird. That's something I remembered. And what else? And it's very prone to get like you can easily feed training data set into validation with TensorFlow. I mean, there's no check for that. And I remember when I trained a neural network for some things, like I was saying, oh, the validation process, the validation accuracy is so high. I mean, I can publish a paper. And later on, I noticed that, oh my God, I was feeding training data set into validation process, which TensorFlow didn't let me know. But with Keras, it's not that easy to make the error. So that's why I recommend using Keras other than TensorFlow itself. And also, if you program TensorFlow, you have to manually manage the devices, like dispatch different type of computations into different devices. So using Keras, introduces much less problems. Oh yeah, I remember the word. Okay, so I was talking about the inverse problem, right? And I was going to give us example like the Big Bang. So I know some cosmologists were using deep learning using deep learning methods to simulate the Big Bang. And that was an inverse problem. And I just couldn't like recall that word Big Bang. Okay, Big Bang. Sorry.
Okay, so it's almost 3:30 now. So I wonder if anyone has more questions either on the afternoon sessions or on the morning sessions. You want to maybe type in the chat, or you can also reach out us by email after the sessions if you want to concentrate on trying exercise right now.
Yeah, I think Zal, most of them are trying to run the notebooks right now, I think. How long will the accounts be active, these temporary ones that were created?
Wait, it's till 5 p.m., right?
Yeah, I'll reset them later this afternoon. So they'll be active until 5.
Until 5 p.m. today? Okay.
Yes. If anyone participating wants to go ahead and sign up for a TACC account and has any questions about doing that and getting an allocation on one of TACC resources, feel free to reach out to me.
So Zhao, if you stop sharing, I can share the instructions for them to run the morning example on Frontera for those who are interested. So again, the basic setup is exactly the same. You would SSH into Frontera instead. For the copy command, this is what you ran on Stampede. But on Frontera, the path is slightly different. It's scratch 1. The rest of it is the same. The setup script has been modified there to install the TensorFlow GPU. Running the notebook is exactly the same. So that's just the scratch of the scratch 1 is the difference of Stampede and Frontera the steps. So to get the notebooks and the data set into the copy command can take a while because it has the data set. I haven't set them up separately, so I'll make sure I do that for the next one. But the copy command could take a while. You just could take a few minutes. Just wait for it to cleanly finish, and then or you can just copy the notebooks and change the path internally. That could also work. So just run through these same steps on Frontera. And then you already know how to launch a notebook and so forth. And the same examples that you ran in the morning, those will work on Frontera. You would have to use the RTX queue and the reservation information that was sent to you. So Jason, do they have the reservation information for Frontera?
I think it's the same name.
Same name? Okay.
UTSA. So,
okay.
Yeah.
So here, instead of SKX normal, you would use RTX in the queue name. And the reservation name is the same. Same for the project name. And just make sure your system is selected as Frontera. So I'll just, don't forget to complete. So basically, in your copy of the slides, slide 51 and 52 from the morning slides, just rerun those steps on Frontera. And open a notebook, and you should be able to run those examples on GPU.
So Amit, can you also update the PDF version on the Google folder drive we put them
Yes.
in?
Okay.
Okay,
Will do.
thank you.
Yeah.
So Zhao, if you have any updates of your slides, and you can also make updates on the Google folders. So does anyone else has any question?
Weijia, can you post that direct link to the Google Drive slides, or
Sure.
just send it to me directly?
There's one question.
Yes. In the chat, 1 second. So the TensorFlow you can install in your user area. So in the setup script, you would see that basically you would use pip install -- user command, and that installs it in your local Python area. So you could try out different versions of TensorFlow. It's basically installed in your local home folder, and that's where Python would pick it up.
It looks like there are no further questions, or I think there's one more question from Hamid.
Yes, 1 second.
So for the different version of the TensorFlow, I think like even in our tutorials, you need to install your own TensorFlow there. So in general, in TACC, and we have a module system. So that's where we can actually hide the different Python installation in there as well. So if your TensorFlow require different Python installation, you can see if we already have that one installed. If we do have that one install different TensorFlow is you can install them on your home space. So you can install different version of it. So if you're asking for other software, so let's have like a Python package, it doesn't really require elevate the privilege. You can install them pretty much on the user space that you can do whatever the version you need.
Yeah, Vesha, so I had answered that question. I think the second one was how many nodes can be allocated to a user? Is there any limit on that?
It's different. It depends on the different queue and the different project. So we for both Stampede2 and Fronteras, and we have a user guide that you can referring to. The user guide has a more detailed information on how you can submitting jobs and how you can run different jobs. We do have a different number of limitation on both number of nodes you can request, as well as the length of the job, each job it may take. So you can referring to the corresponding resources and the queue to see what that limit is. If you require more nodes than what we are currently limited, you can also write a ticket and or contacting us. So we may make like a one-time request, like reservation for you, so you can run a larger job.